Okay, in this video, I will describe about the first approach in model selection, which is to use model selection criterions. But first of all, I would like to provide some overview about the concept of training and test error. These are indicators of the goodness of fit of your model. But in the experiment, you see that when you have a training set. This is the set of data you use to estimate a model. But then you also have questions about because the model is trained in some optimal sense. For example, linear regression model is the parameter is selected so that the residual error is minimized, which means if you evaluate the MSE on the training data set, it is at minimum, right? That's why, but you want to evaluate or assess the model quality in terms of how does it generalize to unseen data set. Okay, that's why we have another data set. This is called test data set, and you would like to approximate. You would like to use this data set to approximate the true test error. Okay, so in these scenarios, we observe these typical U-shape. This is called typical U-shape of generalization error, which is indicated in the green line. Okay, when you perform an experiment on varying model complexity, sometimes people use the term model capacity in machine learning. You can think about model complexity as well. As you increase, for example, the order of state space equation, you put more layers in your neural network, right? More number of neurons. What else? You use more features, right? More features in linear regression model, which means complexity is larger. You will see that the training error is typically decreasing over complexities, because your model now has more flexibilities, has more degree of freedom, and it allows your model to adjust and learn the data better and better. That's why the training error is less. But if you use the model, you use the train model to evaluate on the test error, and then you evaluate it. Okay, this is called generalization error, which is in the green line. It is typical that you will see the characteristic of U-shape here, which indicates that at some point of the model complexity degree, your generalization error start to rise again. Okay, in this typical U-shape, we call that such condition as overfitting, which means your model complexity is now too high. All right, the detail. All right, the the flexibility of your models that you allow it to be large, it tends to learn unnecessary characteristic from noise instead of learning the true characteristic of the true representation of your model. Okay, and of course, if your model complexity is too low, probably this zone, okay, the training error is still high. Generalization error is still high. We call this condition as underfitting, which means your model complexity is still too low. Is too low, which means it lacks flexibility to learn the true representation of your system. Okay, and so people refer to this U-shape when you perform the experiment. Okay, I illustrate this concept, all right, with some example of fitting AR model. The true representation is also AR, okay, with order 5. So I use this AR model to generate time series, and I also use AR model to fit the data using the least square method. Here I only plot the training error. All right. So I plot the loss function, which is MSE, as I vary the model order. Okay. And you see the trend that the minimized loss, the MSE is decreasing. Okay. But then as P increases, the model tends to here from order 1 to order 2, and the second order to the third order, you see that there's a significant gap in the MSE reduction. That which means your model, as you start to increase the complexity, it tries to pick up relevant features in the data. Okay, but then you see the gap is basically decrease until model order 6. It doesn't seem to improve the complexity that you added doesn't seem to improve the loss function MSE. Okay, so in practice, this is the phenomenon in the training MSE that I say that it's supposed to be decreasing. So if you observe this, you can you can generally see that, oh, probably this is gonna be the complexities that they're not favorable because it doesn't improve the loss function significantly. Okay. So basically, we look at the knee. The kind of a significant gap in the loss function improvement. So in this example, now, okay, let's see. We have it's basically data fitting problem. Fx is the true representation. So we generate the data in this way. This is a true representation. Corrupted noise, your measurements. When you perform a modeling, okay, you propose f hat. And the f hat in this experiment is one of the 3 choices: linear model, quadratic linear model, basically linear polynomial, quadratic polynomial, and the last one is smoothing spline. Smoothing spline is basically the piecewise polynomial function. The way you fit the smoothing spline is that you decide how many interval you have. This is called a knot. And then for each interval, it can be some polynomial function. That, of course, polynomial function in each interval will have different coefficients. All right. Suppose in this interval is let's say 1 plus x squared. For this interval, it might be x squared plus 0.1x 0.2, for example. These are parameters to be learned in the smoothing spline, and also the location of the knots. All right. So as in terms of specifying the model structure of the smoothing spline, user get to use the number of knots. Okay, the number of knots in the smoothing spline, and probably the polynomial order. Okay, so smoothing splines. So if I pick more number of knots, what does it mean? Is the model more complex or simpler, Totok?
More complex อาจารย์
more complex, right? Because if I say, oh, 100 knots, so it means that I just kind of discretize this interval into 100 intervals, and I allow each of 100 intervals to be different polynomials. So my smoothing spline has more complexity. So basically, the labels in the experiment here, I start from a simple model, right? A quadratic model is more complex than a linear one, and the smoothing spline is the most complex one. So you see the graph fitting. So if we look at these top planes, the left one is the fitting on the estimation data. The right one is on the test data. Okay, what do we see? The red dots are data points. The black one is the true representation. From this graph, okay, which one performed worst? Pink. Which color and what model?
The blue one.
The blue one. And
Yes.
from what model?
Linear.
Linear. Okay. Which one seems to capture the dynamics of the data points the best? Pink?
The for the estimate data, the best
Yes.
one is smoothing split smoothing spline.
Spline. Which color?
The orange.
The gold color, right?
Yes,
So
yes,
it
yes.
seems that the smoothing spline has like its data its curve is kind of has a high fluctuation. It tries to capture the variation in the data point, right, up and down. Okay, that's the first thing we discover. But then I would like to for you to take a look at the test data. Okay, can you all suggest? This is the true data generating process. My y has the relationship with x through a representation f, and it has corrupted noise. All right. Okay. So when you take a look at the test data, okay, if you plot um, okay, so the black line, which is fx, the black lines between the plots of the black lines from the left panel and the right panel, are they supposed to be the same, Napat, or they can be different?
Uh, it should be different.
It should be different. Why?
Because the test set and the training set อ่ามันคนละเซตกันแล้วมันไม่โอเวอร์แลปกัน
Uh, no. Okay, first of all, the red dots are data points, right? The red dots are data points. The data points from estimation data and test data are not the same, right? They are not the same. They are different data sets. But I'm asking about the black line, Napat, is the black line represent fx. Okay, everyone understand how this experiment was conducted, all right? I have my true representation fx. Of course, this is practice. In practice, it is unknown, but this is simulation to verify the concept. For example, I put this is just some example. I forgot my math formula. Suppose I say y is sine x plus e, which means the true relationship between y and x is supposed to be sinusoidal curve, right? but the data point doesn't look like the exact sine curves because it has corrupted noise. That's why you see the red dots. It has the trend, it lies on the trend of the black line, but it is not exactly on the black line, which is the true F. Okay? Of course, in the data generating process, of course, the noise is a random variable. You observe data from one time, one realization. You get one realization of Y, and that's how you get on the estimation set the red dots here. On the other hand, you observe this system again, this data generating process again. The noise on the new realization are not going to be the same anymore because this guy is random. That's why in the second time or another realization, you observe it again. The only thing that changed is the noise, right? Which means in this graph, the black line still the same because the black line is a true relationship between X and Y, but it's just the noise. It's just the noise that corrupted here. Okay? So the black lines of these two graphs are the same. I just plotted with different scales, different span in the X and Y axis. That's why it doesn't look like exactly the same, but it is the same graph. It's just the noise, right? For example, yeah, the example here, the gap between here, between black line and the red dots, that's come from noise. So you see that the noise E1 on the estimation and the noise E1 in the test data set are not the same. And they're not supposed to be the same because they are random. Okay. You see the pattern of the data points are now different in the test data set. Now, what do you observe in this graph? Who perform smoothing spline capture the data points quite well in the estimation? What do you see in the test data set, Toto?
It's occur overfitting.
Overfitting?
Yes, because between minus 0.2 and 0, the valley indicate that it's overfitting in this way.
I think it's just too soon to say that it's overfitting because I mean only from this graph all you can see is that it fits poorly, right? It doesn't seem to capture the red dots anymore in this graph. Okay, so the smoothing spline, its performance on the test data set is not as well as it did on the estimation data. If you look at the graph fitting, all right. But then now I would, this is just to see overall fitting. But then if we evaluate the fitting error or the MSE, okay, and then we we vary the model complexity. So I vary the model complexity of the polynomial models. Okay, one is linear, right? Second order is quadratic. The blue one is the blue one is estimation MSE. The red one is the test error, the test MSE. For polynomial model on this graph, do you see the U shape again? That first of all, we see that MSE is always decreasing, right? Always decreasing, and the test MSE, the generalization error. Now you see this phenomenon that the test error now it's decreasing, but at some point it starts to increase again. That's the U shape, and that's what this is a overfitting zone. Okay, for the polynomial models. Also, the smoothing spline, you also see the same pattern. The MSE, the train MSE always decreasing, but the test MSE has, start to increase again. Okay, so this is how you observe overfitting. All right, overfitting is something that you observe by take a look at the train and the test MSE. Okay, and see if you see the general the U shape on the test MSE. The next question is, does overfitting always occur every time we do the model, or does it always? Do we also have this kind of observation regardless of the model choice, regardless of the true representation of the model? Okay, so this experiment, this simulation, try to answer that by considering again, you vary the model complexity, just like the previous example, linear, polynomial, smoothing spline. Okay. We're going to take a look at the test and train MSE. But now we're going to split into two cases. The first one is when the true representation is nonlinear. Okay. Y equal fx plus e. We do the same experiment, but one case is your f is nonlinear. Nonlinear model represents somehow like a more complex representation than linear one, right? So the second case is when your f is very close to linear one. Okay, so when f is nonlinear, again in this graph, which model fit the best? Napat.
Smoothing spline.
Smoothing spline, okay. It seems to fit the data points best, right? But as
Yes.
again, as I mentioned that the black line is the true representation, it seems that the green one, the polynomial one, can somehow align with the black line, right? Okay, but not to the data points. Again, I emphasize again, in the real practice, you don't know fx, right? You never know the black line. This is the simulation to verify the concept, all right? Okay, if we take a look at the test MSE and everything, now please take a look at we know that the test error doesn't have to be decreasing all the time, right? And in this example, I just vary model complexity like linear one, quadratic, and cubic polynomial. You see that the MSE of the cubic polynomials is bigger than this one. Napat? Oh no. Totok, can you observe about the degree to which the MSE, the test MSE, is increased? It is slightly or it is increased significantly?
Slightly increasing, Ajahn.
Yes, just slightly, right? Okay. Which means if you see this as an overfitting, the degree of the overfitting is tend to be small, right? From this graph. Okay. Now let's take a look at another example. When S is close to linear, the true relationship between X and Y tends to be linear. And the linear things represent something simple, right? Compared to nonlinear one. So that's why you see that the black line, the data points, the red dots tend to be like a straight line in this graph. Okay, and you also see the same, the smoothing spline tend to what? Tend to adapt with the data point, which the data points just located like above and under the straight line, the true relationship. But when we observe the MSE, again you observe the overfitting, but let's see the degree the degree of the MSEs that tend to increase at the higher at the higher complexity. So this gap seems to be much more than the first one, the first case, right? Which means the degree of the overfitting seems to be much more than the case of the true representation. The true representation of your model is nonlinear. Okay, so that's the main message of this experiment. When the true representation is already like complex, is highly nonlinear, right? It should be reasonable when you use a more complex model to learn. And in that scenario, the test MSE is significantly increased. Okay, so overfitting, you will see that the overfitting is more apparent, like it's more can be easily distinguished in the case when your true F is not complex. Your true F is very simple. When your true F is very simple, it means that it doesn't require a complex model. So when you actually use a complex model, you will see the phenomenon of overfitting much more explicitly. Okay, so to make it more relatable, can I suggest some example? Suppose this is the sun radiation, irradiance. All right. Everyone know that solar cell power. Okay, solar power generated from the solar cell. I mean, if you derive some equation, and I mean, of course, some physical common sense, the power is proportional to the sun radiation. Okay, and actually, if you observe the data set, it has a linear trend. Okay, which means in this application, the true representation, even though I say that you don't know, but from the data, from the plot of the raw data, it seems to be linear. Or you can say, oh, it should be close to linear. Which means in this scenario, if you use a deep learning model, which means that the model is very complex, maybe you put 7 layers, all right? In such case, the degree of flexibility you try to add on the model is totally unnecessary, right? Because the true relationship is already linear. You can use a simple linear regression model, probably just first order, second order, that's enough. Okay, so if you use neural network, a very complicated one, to explain this simple relationship, you will observe overfitting easily in the test MSE. That's all what it means from this slide. Okay. So which means that when you choose a model, it's better to get to know the data from your application well. It's not like, oh, one model can perform best for all kinds of applications. Getting to know the data, getting to know the physical relationship is going to help you to develop a model that is suitable for the learning process. Okay. Okay, so next I would like to present two approaches of model selection. The first one, how long has it been? Half an hour. Okay. Maybe I break the video.